So today we're going to go over one real-life application for the first order ODE. Take a moment, pause, and take a moment to read the following statement of the problem, and then we're going to go over some details on how to actually come from the description of an experiment and setting up a differential equation, and then finally answering some questions. Remember, in real life, differential equations are designed to simulate or model a process that depends on time, and then of course based on that simulation with the differential equations, then you can answer some questions that you might be interested in with respect to that experiment. So imagine you have a tank, like a recipient, right, that contains 20 pounds of salt dissolved in 100 gallons of water, and a salt solution of the same kind with concentration 3 pounds per gallon flows into the tank at the flow rate 2 gallons per minute. And then the well-stirred solution is drained from the tank at the same flow rate. And then you have a bunch of things to find. Let's focus on the first part. We need to find the amount of salt at time t. Before you write the equation, it's very important to establish what is your dependent variable. So there is a process that depends on time, this flowing of the mixture solution, and then we need to find a quantity. And that quantity is given here in the request for the problem. We want the amount of salt at time t. So I can't emphasize this enough, because most people have troubles writing the differential equations by not paying enough attention to the meaning of the dependent variable. So t is the time, that's pretty obvious, but what is the dependent variable? What is y of t in your problem, right? So y of t, as the problem requests, will be the amount of salt at time t. So because this is measured in pounds, you want y of t to be the pounds of salt at time t in the tank. That is the meaning of y of t. So, by the way, if I am going to set up a differential equations for y of t, dy dt will be measured. Pause for a moment and try to answer, but obviously that's going to be a rate of change of y with respect to t. Y is measured in pounds, so this is going to be pounds per minute, or whatever the time unit measure is here. Let's say it's minutes. I mean, it is minutes, it's given in the problem. So dy dt should be in pounds per minute. Let's also pay attention to the keywords here. So the tank contains initially something, right? That is going to be an initial condition in the problem, not part of the differential equation. Once you establish a differential equation, whatever the information is given here for the word initially, that is part of the initial condition. That, in other words, the amount of salt at time 0. So I can actually already write it down here. Mathematically, initially, I have 20 pounds. That means y of 0 equals 20. Okay, so that's the math translation of the first phrase in the problem. Furthermore, it says that the flow rate that comes in, which is 2 gallons per minute, is the same as the flow rate out. That means during the process, the amount of fluid doesn't change. The salt dissolved in the fluid does change. But if you start with 100 gallons of fluid, you're going to stay with 100 gallons throughout the process. So once again, pause and make sure you understand what I'm talking about here. The amount of fluid, it doesn't change. What does change is the salt. Okay, because you start with a certain quantity of salt in the tank, and you pour in a different concentration of salt, expressed as pounds per gallon. So if you want, you can draw a little picture here. Let's say this is the tank. It will always contain 100 gallons because, as I said, the flow rate is the same. What comes in the tank, you have 3 pounds per gallon, the concentration, the flow rate 2 gallon per minute. So this is the stuff that comes into the tank, and then what comes out of the tank, you need to express in the same way. So you notice that the amount of salt that comes in is expressed in quantity per gallon and then gallons per minute. So I have 3 pounds in a gallon, but in a minute I have 2 gallons coming in. So basically in a minute I have 3 times 2, which is 6 pounds per minute. Now, what is the concentration that comes out of the tank? Well, that concentration is not fixed. Again, that's the typical part that people sometimes get confused about. Y of t is the amount of salt in the tank. Now, how much is per gallon? I don't know, right? I mean, but it's expressed by Y of t. So if at time t I have Y of t pounds of salt, that means the concentration in the tank will be Y of t over 100 pounds per gallon. Okay, Y of t is the overall amount of salt in the tank. In a gallon, I'm going to have Y of t over 100. So you want to express what comes out of the tank in the same manner what comes in the tank is expressed. Concentration, flow rate. Concentration, flow rate. Now the flow rate out is the same, so it will be 2 gallons per minute. Right? The quantities 3 and Y over T over 100 again represent concentrations. The only difference is that the concentration that comes out will be continually changing, right? I mean, because you start with an initial quantity, but because of a different concentration coming in, the concentration in the tank keeps on changing while this process continues. All right, so how do you write the the differential equations for the change of the salt in the tank? Well, you write with plus whatever comes in and with minus whatever comes out. So what comes in is the concentration in the tank times the flow, to which you subtract the concentration out of the tank times the flow rate out, which again in our problem is the same. So in our case then dy dt, or y prime if you want, it's concentration that comes in, which is 3 pounds per gallon, multiplied by 2 the flow rate, which is gallons per minute. By the way, later on you don't have to write the units. I just want to make sure you guys understand why this makes sense in the end in terms of the units. Concentration in the tank at time t is Y over 100, which is again pounds per gallon, and the flow rate is 2, which is gallons per minute. And so notice that the gallon units will cancel as expected, because remember what I told you, dy dt should be pounds per minute. You know, how the salt changes as time goes on. So y prime, if we simplify this, becomes 6 minus 2y over 100, or 6 minus y over 50. And together with the initial condition y of 0 equals 20, this is the initial value problem, which will give me eventually the amount of salt in the tank at time t. So this is setting up the equation. Now we just go about and solving it. Again, pause for a moment and make sure you understand how the equation is actually established. So I think we have room to write it down here, the solution. If you do it correctly, I mean, if you set it up correctly, then you will have basically an equation of first order with constant coefficients. Remember, that can be solved very quickly with the two-step method, right? So I mean, you can look at the homogeneous part. The non-homogeneous term is 6. So the homogeneous part is y prime minus equals minus y over 50. So the homogeneous part of the equation is c e to the minus t over 50, right? Because that's an exponential ODE. The particular solution is in the form of a constant. If y prime is 0 and you solve for y, then the constant solution yp would be 300. 6 times 50, 300. So the general solution of the ODE is c e to the minus t over 50, which is the homogeneous part of the solution, plus the particular solution 300. Remember, that's an initial value problem. You start with an amount of salt. So that means you impose the initial condition now. Y of 0 equals C e to the 0 plus 300. And that should be equal to 20. The initial quantity. So that gives you the value of C, which is 20 minus 300. That's minus 280. So finally, the answer to part A, what is the amount of salt at time t? That's the exact solution of this ODE. Minus 280 e to the minus t over 50 plus 300. Now, the second part of the problem was, what is the steady state amount of salt? So the steady state amount of salt is y of t, the limit of y of t, as t goes to infinity. That means if you let the process go on for a long time, what is the limit, the limiting amount of salt in the tank? So notice that as t goes to infinity, the exponential approach is 0, right? E to the minus infinity is 0. So therefore, y will approach 300 pounds. So in the long run, you're going to have 300 pounds of salt in the tank. By the way, that's not a surprise. If you think about that, eventually the concentrations will equalize. What comes in is going to be equal to the concentration in the tank if you keep on draining the solution. So if the concentration that comes in is 3 pounds per gallon, and you have 100 gallons in the tank, in the end you have 3 times 100. And so that's not a surprise that the steady state amount of salt is 300. So that can be answered from physics. If you only care about a steady state amount, you don't need a differential equation. You need a differential equation to control the amount of salt at any point in time. But in the long run, it will be 300 pounds. Finally, the last part of the problem was to determine the time when the salt will be 200 pounds. So how do you do that? Well, you're going to set up the solution 300 minus 280 e to the minus t over 50, set it equal to 200, and solve for t. You may need to use the calculator here. So minus 280 e to the minus t over 50 is 200 minus 300, which is minus 100. Isolate the exponential, which is 100 over 280. Take the natural log on both sides and simplify. So minus t over 50 is natural log of 100 over 280. Again, take your time with the calculator to do this. And then t, you multiply by minus 50 both sides. And with the calculator, t should be approximately equal to, I did it here, approximately 51 minutes. I had to take a peek for that, so I didn't have the calculator with me. So 51 minutes approximately should be the time value until the solution gets to, until the quantity of salt gets to 200. So in the second part of the, we're going to have a short second part of this, just another problem with a different data to set it up. And for that one, we're just going to find the general solution. But all the problems in this section are similar to this one, just with different numbers. So more on this on the second part.